something like that. And we said if you have a high power of a trig function, it's not too high, you can use a reduction formula, and maybe it's best to let a machine do that, because after you get about to 6th power, there's too much chance of a mistake. But if it's just 2nd power, you can rewrite it with a trig identity. This suggests that some of these other trigonometric integrals might also fall to trig identities. Here's another kind that comes up. You might say, why are we doing these particular ones? Why not do x to the sine 10th or something like that? The fact is that these are integrals that come up in practice quite a lot in the sciences. And also you'll see in this class, some of our other techniques take common integrals and by a substitution reduce them to integrals of this form. So these are actually very important forms, even if they seem kind of arbitrary at the moment. We'll say that being able to integrate powers of trig functions is an important concept. Here's another one that's an important concept. Suppose I have integral of sine, big thick pin here so I can see online. Just can't do it. Sine AX cosine BX. BX. Suppose I need to do this one. Anybody guess how you might do that one? This is a pretty tricky one to guess. The trick, again, is a trig identity. So trig identities apply to these 2nd powers. They also apply to sine times cosine. Or if you have an integral of sine times sine AX, sine BX, or an integral cosine AX, cosine BX. The trick is to think, where in trigonometry did I see those kind of expressions before that I could rewrite them? All right. One hint is to say, well, if I took sine of A plus AX plus BX, let's write it that way. Remember a formula for the sine of the sum of two angles? It's sine cosine plus cosine sine, right? So this will be sine AX cosine BX plus cosine AX sine BX, right? Well, that looks, the first part's right. How do I make it look like just the first part? Here's the trick. You can take the difference formula, sine of AX minus BX, and that one gives you the same thing with a minus, right? The moment I stop asking a question, it goes out. Doesn't matter how many pins are in. Sine AX cosine BX minus cosine sine, right? So those are trigonometry sum and difference formulas. And now if you take the first one and subtract the second one, these bad parts cancel, and you find out that this one minus this one, using these formulas, the integrand here can be rewritten as this first one plus the second one, so that these cancel, divided by 2, so that you get one half of this twice, right? So you find out that sine AX plus BX minus, or plus, excuse me, sine AX minus BX gives you this plus this, twice what you want, so you divide it by 2, and you simply replace the integrand with this by a trig identity. And this is integrable, right? You can integrate sine easily. Maybe you can see by trig identity what you could do if it's sine times sine or cosine times cosine for the same token, right? Well, suppose, for instance, I want to integrate. Yeah.
Can't you also rewrite it as the integral of sine ax plus the integral of cosine dx? Or is the integral not separate?
Technically you could, but it's more complicated if you want. I mean, the sine and the sine is the easiest because those are the trig identities you memorize. There's another one that says sine of any angle is pi over 2 minus the cosine. So you can rewrite this as cosine pi over 2 minus all this stuff and integrate a cosine instead, yeah. So more trig identities, yeah. He's asking if you can write this as a sine plus a cosine. Only if you do another trig identity in addition. So let me look at this one. If I have an integral cosine times cosine, for instance, what do I do with that? That's actually the same trick because we know that cosine ax plus bx, cosine angle plus angle, cosine of the sum is cosine cosine minus sine sine, right? This is why you take trigonometry before calculus. And if you take cosine ax minus bx, that's cosine cosine plus sine sine. Now you add those two together and divide by 2. I add them together to make these parts cancel the signs, and then I wind up with just cosine cosine and cosine cosine. So if I add these two together, cosine ax plus bx plus cosine ax minus bx. What do I do? What do I get? These two cancel, and I get twice this, twice what I want. Twice cosine ax cosine bx, right? Now, so I just got to divide this by 2, and I've got the integrand I want. And so I replace this integrand, this thing, cosine x cosine bx, with this one. Cosine ax plus bx plus cosine ax minus bx, all divided by 2. These I already know how to integrate. Integral of cosine is sine. Integral of cosine is sine. Kind of a constant here in this case. But the idea is you do similar to here. When you see integral cosine squared, you just memorize from experience. You rewrite it by the half angle identity. When you see an integral of a cosine ax cosine bx, sine ax sine bx, cosine x cosine bx, you replace it with the trig identity. You can probably figure out how to do this one now too. If you just took this one minus this one, well, these terms would cancel, and you get the sine, twice the sine times the sine, and you divide that by 2. So this one falls similarly by subtracting these and dividing by 2, all right? That takes care of all those integrals that actually come up a fair amount of the time in practice. Now we just need an example. But trig identities really help you to make functions we don't know how to integrate into functions we do know how to integrate. So let's try this one. Cosine 3x, sine 3x cosine 4x. All right. How do I do that? I remember that if I have a sine ax cosine bx, I can use the trig identity and immediately rewrite it as from the sum and difference formula, sine of 3x plus 4x. That'll give me sine cosine plus cosine sine. And I subtract off sine 3x minus 4x. That'll give me sine cosine minus cosine sine. So I'm just left with a sine and a cosine. Divide that by 2. I get 2 of those. This was the trig identity we wrote first there, with a equals 3 and b equals 4. You can replace this integral with this integral, right? Now you can do that, right? Because this is integral of 1/2 sine 7x minus 1/2 integral sine minus x. Like that. those I can do. It might behoove me to take this minus here and say sine is an odd function, so I can pull the minus out, right? Remember this one, I also, another trig identity. Sine of minus theta is minus the sine of theta. The minus comes out because it's an odd function. This minus can come out and cancel that one, so let's put plus plus, right? I'm also using this identity in there. Now, integral of sine 7x is minus cosine over 7. And I have a half out front, so I put 1/2 minus a 7th cosine 7x out of memory. Integral sine kx is 1 over k cosine, minus 1 over k cosine kx. And this one I've got 1/2 minus cosine x has derivative sine x. And then plus c since I've dropped my last integral sign. And you can simplify that a little bit to minus a 14th cosine 7x minus a half cosine 7x. Maybe we should write that down just to be complete. So the simplified answer on that one now is minus 1/14 cosine 7x minus a half cosine x plus c. Yeah. You subtract them. I kind of memorize in my head. The sign of the sum is sine cosine plus cosine sine, right? Sine cosine plus cosine sine. This one, the difference is sine cosine minus cosine sine. And so if I add them, then these parts cancel, and I get twice sine cosine. And so I'm going to add them and divide by 2 to get sine cosine. That's the idea. Did I write enough letters in here? This is what I kind of think in my mind when I do this. So I will add them so that these parts will cancel, leaving with sine of the first one, cosine of the second one. If I subtract them, then I get cosine sine, or cosine 3x sine 4x. So you can subtract them if you put the cosine and sine in the other order. That's what you can kind of do is picture these trig identities in your head. All right, that's the next one. Like what Macaulay Culkin said, have you had enough or are you thirsty for more? Movie. He said that very well. It's hard to believe he's all grown up now. All right. Now the next one is this. We're just getting a whole bag of tricks here, and the idea is you're developing experience. It's kind of like ice skating. You go out and you have to learn all these different moves, and then you have to put them all together to be able to actually do anything, right? So that's what we're trying to do. Let's do, just as a simple example now, something a little trickier. Suppose I had, there's a couple problems like this just to sort of throw a red herring in here. So this one is a red herring. It kind of looks like these others, but it's different. You see sine 2x cosine cubed x. So some of these are just ad hoc techniques, meaning just for the particular problem. Other ideas I'll put for this one. This one is not a standard formula. I don't say memorize this one, but you want to see a few of these to realize, oh yeah, that's clever. You want to have a cleverness factor going on in this. How can I do this one? It's not sine ax cosine bx because this one's cubed. It's not sine x to a power and cosine x to a power. I could do it by another method that's coming up. Right? If it was sine squared, I could do something. Here's what you can do with this one. You have a trig identity for sine 2x. Recognize you can rewrite that as 2 sine x cosine x. Right? That's the trig identity for a double angle. And then all times cosine cubed x dx. What can I do with this one? Pull the 2 out. That doesn't hurt anything. In fact, let's pull a minus. I'll pull 2 out. And then we'll say this is cosine to the 4th of x, 4th power, times sine. Does that give you a hint? Part of the trick is just to do enough of these you recognize it. So I'm trying to get you to think about this. So cosine times cosine cubed is cosine to the 4th. Here's what you can do. Here I have a function of a function. It's the 4th power function of the cosine. That suggests maybe a substitution u equals cosine x would work. If I let u equal cosine x, then du must be the derivative of that dx. It's minus sine x dx. Right? Oh, it's just what I have to within a constant, minus 1. So I can fix it. I'll put a minus 1 outside, cancel it with a minus 1 inside, and there's my du. So this falls to u substitution once I make a trig substitution, right? A trig identity. Say again?
Why is sine x?
Oh, I put a minus in here and canceled it with a minus out here, and the reason is so I'll get minus sine x dx and can substitute this out and put du. I can leave the minus off and put minus du. Let's do that. I'll put minus du is sine x dx what I have in there. And then I can leave these minuses off and I'll just call this minus du. That works too.
I'm trying to find out why it was negative.
Yeah, I tried to put a negative in here so I could substitute du. So I put a negative inside and canceled it with a negative outside, so I think I could just do my substitution. That's all. It wasn't negative. I just took it over here. It wasn't negative.
Oh.
And then I put it in so I could substitute, and canceled it outside. So it would, yeah. So let's just do it this way. Let's say if u is cosine, du is minus sine x dx. That means minus du is sine x dx. I'll substitute this out with minus du. That works too. And this is u to the 4th. Trouble with mathematics, you have to think a long time on those things.
I just
Oh, derivative of cosine is minus the sine, right? That's where it's coming from, yeah. Yeah, so du is the derivative of cosine minus sine times dx, yeah. That's what, okay, I was answering the wrong question. All right, so this is now twice the integral of u to the 4th minus du. You can take the minus out, right? And take this as minus 2/5 u to the 5th plus a constant, where u is cosine. So you've got minus 2/5 cosine to the 5th of x plus a constant. That's the function that has this derivative. So sometimes there's other things that don't fit into these fast formulas that you can just think for a second, maybe get the trick, right? So I put that one up. There's a few problems in the book like that. I can't remember if there's one like that on your actual homework or not. If I had more homework, I'd make sure there's stuff like that on there. But that's a trick. All right. Here's another one. Suppose I had integral of sine squared x cosine squared x dx. How could I integrate that one? Anybody see that? There's actually more than one way, but we'll say, based on what we've been doing, there's a particular trig identity I want to apply. Yeah, there we go. There's another trig identity. Sine squared plus cosine squared equals 1, so sine squared can be replaced with 1 minus cosine squared. Now, if you multiply this out, it's integral cosine squared minus cosine to the 4th. You can break it up into two integrals. Integral of cosine squared minus integral cosine to the 4th. And this one falls to the substitution 1 plus cosine 2x over 2. So you replace this one with 1 plus cosine 2x over 2. Do that one. And this one, you can use the reduction formula, right? A little harder. I'm going to leave that off. Well, that's how you can deal with those sometimes. If you just have a square in here, you can sometimes replace it with 1 minus the other one squared. Alas, that's not the end of the story. Any questions on that one? Yeah. Sorry to erase it. Maybe I could leave the last part down. I can never write fast enough to keep up with this stuff. So here's another one. Now, here's another rule coming up, though. I try and box most of the rules. I should have boxed that one with sine AX, cosine BX, those three in the beginning, because those are the ones you want to memorize. You just use a trig substitution. Now, here's another handyman trick, if you will, again, for integrals of sine, a little more exotic than the last one, sine mx cosine nx, and it doesn't have to be x as long as it's the same argument, dx and bx or something. Cosine nth power x. In general, sometimes you can do it by those tricks. So we'll say more generally, here's a trick you can use, and it works like this. It's very similar to what we did in the last one. If m is odd, the power of sine, you can make a trick like we did in that last one and let u equal the other one, cosine x. Well, if the power of sine is odd, you can let u equal cosine. Or if n is odd, the power of cosine, you can let u be the other one, sine. Whichever one is odd, let u be the other one. And this works pretty well. You can even use it to a certain extent with negative powers. But what we need now is an example. So suppose I do, oh, by the way, if both of them are odd, then you can let u equal either. Right? It will work, and you'll see why here. Suppose I want to integrate integral of sine cubed x cosine to the fourth x dx. This is actually easier than the last example, believe it or not, because I don't need that long reduction formula when I'm done. The last formula we did was actually harder, right? Because u and m and n were both even, and this rule just doesn't work if they're both even, right? So the last example we did it the other way when they're both even. But when at least one of them's odd, we can do this trick. Since the power of sine is odd, I'm going to let u equal a cosine. With u equal a cosine, then du is the derivative of cosine dx is minus the sine of x dx. That derivative of cosine is minus the sine. And now, I need a sine x dx, but I don't have it. I use what I call Howell's rule here, right? Remember Thurston Howell from Gilligan's Island always got everything he wanted. What did he say when he couldn't have what he wanted? Or when something didn't fit? Remember that famous line? Doesn't fit, break off a piece and make it fit, right? So that's what we're going to do. Sine squared x, cosine fourth x, times, and I'll put a sine x over here. So now it's still the same integral, sine squared times sine is sine cubed, but now I have what I need multiplying dx except for the minus, so I'll put a minus here and cancel it outside with a minus outside like I started doing in the last problem. So minuses could go away if I wanted. But now with this substitution, this is du. And what do I do with sine squared? Yeah, I'm going to replace it with 1 minus cosine squared again. So the power of sine that's left has to be even since it started odd and I took one out. So I'm going to replace it with 1 minus cosine squared to a power. I'll just get cosines in there. And now I can rewrite this as minus out front, integral 1 1 minus cosine squared is 1 minus u squared by the substitution. Cosine to the fourth is u to the fourth. This just becomes du. I can integrate that, right? It's a polynomial. Multiplied out, it's integral minus the integral of u to the fourth minus u to the sixth du. What an easy one to do, right? Probably the one I'll miss. I have a good story for you on that. Yeah.
Before you do that, I have a question. So, how come you just didn't set u equal to cosine 4x and then have du be sine 2x?
If I let u, the question is why didn't I let u equal cosine fourth x? If I do, then du has to be the derivative dx, and the derivative by the chain rule is 4 cosine cubed x times minus sine x. Then I have to multiply it by dx. So I can do that if I have this stuff now multiplying dx, but it's right, I don't. Now I need cosine seventh in here. In other words, if I let u equal cosine fourth, I need this for du, and I don't have it.
So you just have to break it up first. You break that sign off.
Yeah, break the sign off, and then it becomes part of the du, and the rest of it becomes powers of cosine. Yeah.
So what happened to that sine squared?
I'll replace sine squared with 1 minus cosine squared, which is then 1 minus u squared.
Okay. So if you turn that into cosine, then you can use cosine x as u.
Yeah, exactly. So that's the trick here. Now I just have to integrate a polynomial, u to the fourth minus u to the sixth, which gives me u to the fifth over 5 minus u to the seventh over 7 plus a constant, and u is just cosine. So I finally got minus a fifth cosine to the fifth power of x minus a seventh cosine to the seventh power of x plus c. There's this integral. Look at that, I did it in one board. That's what you do if it's a sine times a cosine equal to a power. Okay? Oh, I'm sorry, it's plus. Yeah, she's pointing out minus a minus should be plus. Thank you. Yeah. All right, let's try a similar one. What time it is here? I'm sorry. Suppose I instead want to integrate tangent to the nth power times secant to the nth power of x. What about that one? Those come up less often, but occasionally in practice. So you memorize this formula also. And this formula, again, I should have put a star on the sine to the nth, cosine to the nth. I'll put a star here. It's very similar. This one, if so it's if m is odd, the power of tangent, substitute u equals secant, but this time it's a little different. If n is even, you can substitute u equals tangent. So again, it's substitute the other one, but this time if the first one is odd, you can substitute the other one, but if the second one is even, you can substitute the other one. This leaves the possibility, actually, technically, you think hard about this. If you had integral of cosine to an even power, sine to an even power, you could rewrite them as the power of tangent and secant with some of these powers negative. That's what I did when I was a student. Rewrite it in terms of tangent and secant, and now the powers will come out even, and you can use this substitution. after rewriting sine and cosine powers as tangent and secant powers. Generally, that's pretty difficult. It's longer that way, but it actually does work. So here's the rules when you see tangent and secant. If the first one's odd, let u equal the second one. If the second one's even, use u equals the first one. Now we can do a problem like that. And some of these are real easy. Sometimes by the end of the lecture, you don't know what you could have done immediately at the beginning of the lecture. Here's a good example. What is integral secant squared x dx? How would I do that one? I could say, oh, let u equal tangent x, right? It's even easier than that. What is that? Most of you would have known this at the beginning. Yeah, there you go. It's just tangent, right? Remember your formula is derivative of tangent and secant squared. Just write immediately, oh, that's tangent x, because you always want to keep this in mind. Derivative of tangent is secant squared, right? So that's an easy one, plus a constant. So you just write that one down immediately if you see secant squared. I have to erase my rule here, but we can now try this one. Suppose I had this, integral of tangent squared times secant squared. How would I do that? Another example. Now, it's not an obvious derivative of something. So I use the rule and I say, well, if this one is odd, I make a substitution. Alas, it's not, right? But this one's even, so I'm set. Since this is even, I'm going to substitute u equal the other one, tangent x. That means that I have du equal derivative of this secant squared dx. Now, this time, if I had a fourth power or something here, I'd have to pull off part of this. But it's all sitting here already. I just change that to du. But if it's secant to the fourth, you pull out a secant squared. And, you know what, maybe I should make this harder. Let's do that. I'm going to make this harder. Just to illustrate, because I'm running out of time. I can't do both of them. Suppose it's tangent squared secant to the fourth. I'll say it's even. You substitute u equals tangent x. Du equals secant squared dx. Oh, I don't have quite du, do I? So I use Howell's rule again. I take this as integral tangent squared x, secant squared x, secant squared x, dx. Now the secant squared x dx becomes du. And there's what we call a Pythagorean identity for tangent and secant, analogous to that for sine and cosine. Sine squared plus cosine squared equals 1. Similarly, you remember maybe this one, tangent squared plus 1 equals secant squared, right? That was the Pythagorean identity that's not as well known as sine squared plus cosine squared equals 1. But you use it here. Secant squared is therefore 1 plus tangent squared. I'll call this 1 plus u squared since we're substituting u equals. Let's write it in 2 steps. 1 plus tangent squared by the trig identity. And then that's 1 plus u squared by the substitution. And then tangent squared is just u squared. So I have reduced this to, again, an integral polynomial. I'll scratch this out and put du. And the power of secant there goes away. And now I've got integral u squared for tangent squared, 1 plus u squared for secant squared. And for secant squared dx, I just replace that with du. There it is, and it's an easy thing to integrate. I have to integrate u squared, and I have to integrate u to the fourth. I'll break it up into 2 integrals. I get u cubed over 3 plus u to the fifth over 5 plus a constant. And then you put back u as tangent. This one I do have to erase the first part. Sorry about that. So it's 1/3 tangent cubed plus 1/5 tangent to the fifth plus a constant is the antiderivative I want. Any comments on that one? Okay. Let's put the next one. There it is. All right. What if I have one of these integrals? Cotangent to the nth power of x, cosecant to the nth power of x. Can you imagine what we do with that? This is also a star. You want to memorize this formula. What can I do with that? Complete analogy to what we just did. These things again come up in practice, these powers. Mostly sines and cosines, but also tangent with secant and cotangent with cosecant. You do the same kind of trick. One, if m is odd, it's not dark enough for them. If m is odd, you let u equal the other one, cosecant. Or if n is even, you let u be the other one, cotangent. And then you bear in mind the derivative of cosecant is minus cotangent cosecant. Derivative of cotangent is minus cosecant squared. And you can run with this one also. So it's a complete analogy. So I'll just say you proceed an analogy to what we did for tangent with secant. Yeah.
If you do that with cotangent and secant, instead, is the rule the same?
You say if you had cotangent and secant, what happens is in practice that doesn't come up as much. But the rule doesn't apply anymore because you don't get the derivative of one from the other. What I would do in that case in general is probably rewrite cotangent as cosine over sine, and secant is 1 over cosine, and say, aha, look at that, some of it cancels. Sometimes some of it will cancel, but even if it doesn't, you've got powers of sine and cosine, and it will work with negative powers with a lot of effort. So if you have wrong pairs, then you rewrite them in sine and cosine usually. So this is the integral cosecant, which we can do by our method from last time, similar to integral secant from last time. We can do integral cosecant. All right, so that's got the all the tricks taken care of. I'm a little short on time to finish an example like this. I just say you do it the same way. Maybe I just write the substitution on one of these real quick. Suppose I had, for instance, integral of cotangent cubed, cosecant cubed. What would I do for that one? This one's not even, but this one is odd, so I'm going to let u equal this one. And if this is odd and this is even, you can do either substitution. So I'm going to let u equals cosecant, in which case du is the derivative minus cotangent cosecant dx, derivative dx, right? Well, I need a cotangent cosecant, so I'm going to break one off and call this cotangent squared, and call this cosecant squared times cosecant times dx. And I need a minus cotangent cosecant. this is, I wrote this wrong. I pulled the wrong one off. Sorry. This is supposed to be. I want cotangent squared, and I want cosecant squared, and then a cotangent cosecant is what I need to break off. The idea is you break off what you need for du. Then I need a minus, so I can put a minus in here. If I put a minus outside, now this becomes du. This becomes u squared because that was the substitution. And then there's an identity that says 1 plus cotangent squared equals cosecant squared. That's the trig identity. So you replace cotangent squared with cosecant squared minus 1, which is u squared minus 1. Now you see, again, you've got an integral of a polynomial u squared minus 1 times u squared du. Try that one. That's enough for today then. Time to go. Next time we'll have even more fun with trig integrals, because they do actually come up a lot in wave analysis and other things in higher sciences. Just have to try these. That's the way they work in practice.
Yeah, it reminds me a lot of how I was trig for the first time. We're trying to like prove identities and stuff.
Yeah.
Where you have to try a whole bunch of stuff until you.
Yeah. Yeah.